GANaxy, Galaxy Image Anomaly Detection with Diffusion and DCGANs by Susan Thomas, Ayan Gupta, Michael Wong, Joshua Chung, Oya Randasa, Michael Zhao, and Abe Pukriel.
So in our project, we used DCGANs and diffusion models to identify anomalies in astronomical photos. Previously, unsupervised methods have been explored, but struggle with the high dimensionality of astronomical images. And some implications for our project include we can use our anomaly detection to find B-type stars, extremely redshifted quasars, and other anomalies. And increasingly large amounts of astronomical survey means accurately processing data for novel phenomena is more important than ever. So on the right, you can see some classifications for galaxies, and they include a spiral galaxy, elliptical, lenticular, and regular galaxy. And anomalous galaxies would be galaxies that don't fit the criteria or have imaging errors in telescopes, such as chromatic aberration.
All right, so previous research has attempted galaxy anomaly detection before using a WGAN architecture and encoded images. However, there are some limitations. The first being that their generator model tended to classify noisy images as anomalous. They're linear in nature, which means they're not good for complex, high-dimensional galaxy images. And their models were also not able to create detailed, accurate galaxy images, but rather simpler representations of them. Our solutions would be to implement a diffusion model that can learn to reduce noise in the galaxy images, and then applying that diffusion model to our generator output so that we can improve our GAN overall, as well as using a SimClear, which we'll talk about later on, for anomaly detection with contrastive loss, and generally just applying a more complex GAN structure.
So our goals for our research include using a more advanced complex GAN coupled with a diffusion model for better data generation overall. And we utilize the SimClear model as well as a second anomaly detection model using an encoder. And ultimately, we wanted to produce a state-of-the-art model for the classification and identification of anomalous astronomical images. And as you can see on the right, the DCGAN produced a way more effective image than the WGAN.
So in order to create a benchmark dataset, we used the Galaxy Zoo 1 dataset, which ran from 2007 to 2009, which was an amalgamation of images from the Sloan Digital Sky Survey that was classified into 6 categories. We actually used the Galaxy Zoo 2 dataset, which extended this dataset with additional subclasses, incorporating anomalous images and supplying additional data for analysis, which you can see on the right. We ran an ANOGAN, which is a GAN for anomaly detection, of our images. And our various models used a train test split to provide benchmarks, such as testing mean squared error, accuracy, and other tests that are completely new and haven't been done in research before.
So now let's talk about our GANaxy, which uses deep convolutional layers and anomaly scores to discover new phenomena. Although GANs are typically successful in simpler datasets, the ones that are linear in nature suffer from issues such as low dimensionality, inaccuracies, and produced images. They're not well suited for the high dimensionality of galaxy images. Oftentimes, GANs will face mode collapse, which is where the generator is over-optimized to beat the discriminator, and the discriminator never learns how to tell if the image is accurate or not. To counter these issues, we use the DCGAN. DCGANs have nonlinear structures, such as a sigmoid activation function. The convolutional layers are also able to accurately identify important image features without any classification or labeling. In addition, we also avoided max pooling, which is traditionally used in GAN architectures to reduce dimensionality. Max pooling discards some information, which leads to the loss of fine details. We use threaded convolutions instead, which allow our network to learn meaningful and smooth feature representations while avoiding data artifacts. As a result, our outputs were very accurate in representing real data. As you can see below, our generated images and our real images were very similar. Next, we have to develop the anomaly detection part of our code. In order to detect whether or not images were anomalies or normal, we use the equation AS is equal to alpha times RL plus 1 minus alpha times DL, where AS is the anomaly score, RL is the residual loss, and DL is the discriminator loss. Alpha is the chosen weight for the two losses, or a hyperparameter, eventually being decided as 0.1 after testing. In order to find the losses, we map the images to latent space, which is an abstract high-dimensional vector representation of images. This served as our second framework for anomaly detection, computing the distance between images in latent space.
We also use the SymClear framework, a framework based on contrastive learning that we use to additionally help classify images as anomalous or non-anomalous. As you can see from the graph, the reason we chose the SymClear framework is because in terms of self-supervised learning, it had one of the best performances out of all other models. We used it as another criterion. The way it worked is that it would produce a probability score that depicted how likely each image was to be anomalous or non-anomalous. From this, we could help combine this with our ANOGAN, as I'll explain later on, to help create an overall anomaly score. We trained the data, we fine-tuned the data over our custom benchmark data from the GANaxy Zoo project. So this represents a basic understanding of how the SymClear framework works. Basically, it takes in a random image and performs a series of random transformations on them. This can range from random cropping, resizing, rotating, flipping, or even changing the color saturation. After producing 2 different images with all of these random augmentations applied, it then encodes these images into vector representations. This is represented by the F dot. These vector representations, Hi and Hj, are then projected into a different space to Zi and Zj, from which a contrastive loss can be applied to them. This contrastive loss basically teaches the model that similar images should be paired closer together and dissimilar images should be paired further apart. Overall, this helps the model learn some of the more underlying features that make images similar and hence can be used exactly for a purpose of classifying galactic images. Now, finally, for obtaining the probability score with this model, we use a linear evaluation of the SymClear's output. After the images were encoded and the SymClear model ran over the images, the linear evaluation would output a probability score, giving us how likely the image was to be anomalous or non-anomalous. By doing this, we could couple this probability score or confidence score with the anomaly score generated from our ANOGAN to come up with one giant anomaly score that would help us truly identify which images was anomalous or not. Overall, the reason we did this is because it reduced the dependency on just the ANOGAN or just the SymClear, and overall made our results more accurate and much more reliable to work with.
So we use a diffusion model to be able to reduce noise in images and find the anomaly scores. So how we implemented the diffusion model is that the generator tended to create more noisy images and removed a lot of background features that were important present in the original Galaxy image. And the diffusion attempts to add noise to the image and denoise the image through a reverse diffusion process. And we can see that on the right for the forward. And this allows it to learn the normal distribution like size, color, in order to generate Galaxy images. And we can use this later on to find the discrepancy between reconstructed and original images to be calculated as the anomaly score.
Results and conclusion. Utilizing our GANaxy, we produced extremely accurate galaxy photos, as shown here in Figure 1 on the right. Previous attempts with other types of GANs suffered from mode collapse, limited dimensionality, or speed issues. Furthermore, we used UMAP clustering in order to cluster our datasets. An example cluster is shown in Figure 2 on the right. UMAP is a good fit for our project due to its capability of handling high-dimensional images. It is a framework for high-dimensional graph representations of images in latent space. By running our SymClear model on both labeled Galaxy Zoo 2 data, as well as images from the GANaxy, we achieved an accuracy of 86%, competitive with even state-of-the-art SymClear models. Our SymClear model was able to correctly flag anomalous images, such as images with visual artifacts, or interesting phenomena, such as galaxy mergers, as you can see here on the right, which are examples of some anomalous images.
Finally, in conclusion, we proved that SymClear is a highly effective approach for anomaly detection in Galaxy data. We applied our method to 300,000 images and have identified and cataloged about 8,500 anomalous galaxies. We reached an accuracy of 86%, rivaling even state-of-the-art methods, which are usually 75% to 85% accurate. We did this by using UMAP and latent space clustering to address problems with previous GANs. So why is our research important? Future astronomers can use generated images to expand their data. Our SimClear model is also accurate and quick in finding anomalies. These anomaly detection technique can also be applied to other fields, such as the medical field, for identifying tumors in cancer, for example. Our GANaxy is also perfect for use in other scientific areas needed for image generation due to its avoidance of mode collapse, capability of handling high dimensionality, and more. This model could be adapted to assist in other scientific fields of research, such as medical or forensic investigations. Finally, we want to say thanks to Saurav and Kinjal for providing us with resources and helping us throughout this whole process. We really couldn't have done it without you. We also wanted to thank the Blast AI team for providing us with support and for teaching us so much in so little time. We're now ready for questions.